Okay, so this is one last video on the logs and exponentials. Here are the rules of the logarithms we wrote down last time. So, in particular, log of AB is log of A plus log of B. Log of A over B is log of A minus log B. Log of A to the B is B natural log of A. And log base A of B can be computed as log B over log A, where you take any base. This last one I'd like to write a little bit more about. I'd like to prove it. So let's write down y, whoops, let me change color. Y equals log base A of B. And so I can rewrite that as a to the y equals b, and now I can apply any logarithm to both sides, the base. So I'll apply the natural log because that's the one that we can compute the most easily on a calculator, for example. And so using the properties of the logarithm, then I can bring down the y, and then finally I can just take y to be natural log of b over natural log of A. Okay, and so the log sub A of B is the same thing as log B over log A, and that's really for any base. Good. Okay, so that's how you compute the log to any base on your calculator. There were a couple other things. How about a couple of exercises maybe? So how would we solve for x if we have the natural log of 3x minus 10 is equal to 3? Well, first, the base here is e, so rewriting this directly, we have e to the 3 equals 3x minus 10, and now you can see we can pretty easily solve for x. E cubed plus 10 equals 3x, and then 1/3. Very good. So that's our answer then. Okay, and now how about another one? Solve for x. If we take e to the 2x minus 3e to the x plus 2 equals 0. Well, this is kind of a tricky one. I'm not sure if you recognize this or not, but e to the 2x can be written as e to the x squared. And so if I rewrite the expression like that, does that remind you of anything? Does it look like a quadratic? So that using the quadratic formula, we can solve that. So e to the x is equal to, remember the minus b plus or minus, here I'll write it off to the side, minus b plus or minus the square root of b squared minus 4ac divided by 2a. That's the quadratic formula. So here our a is equal to 1, whoops, b is equal to minus 3, c is equal to 2. And so our e to the x then is going to be 3 plus or minus the square root of 9 minus 4 times 1 times 2 divided by 2. So that's going to be 3 plus or minus the square root of 9 minus 8 is 1 divided by 2. And so e to the x is equal to 3 plus 1 over 2 or 3 minus 1 over 2. So that's 4 over 2 is 2, 2 over 2 is 1. And so taking the log of both sides then, x is either the natural log of 2 or the natural log of 1. By the way, that's the natural log of 2 or 0. Good. So we have two solutions to our original statement. By the way, you can double check what happens if you plug in 0 for x up here. E to the 0 is 1 minus 3 times e to the 0, so that's 1 minus 3 plus 2 is 0. That's true. Very good. Okay. I wanted to also talk a little bit about using some more functions here, some trig functions, and that's the sine function, the cosine function, and the tangent function. And hopefully you remember what the plot looks like for both of these. We'll do them all three. So the sine function has odd symmetry, and it goes up and down like that, right? And then this repeats itself. And so does the sine. So it goes that way too. So this is odd symmetry. And is this function one-to-one? No, it's not. And so therefore, we have to restrict the domain so that it is one-to-one. And the common restriction is between pi halves and minus pi halves. So x is restricted to be between minus pi over 2 and pi over 2. We can include those two values. And so in that case, y is between minus 1 and 1. So similarly, cosine starts at 1 and comes down, and it repeats itself like that. Okay, and again, this is not one-to-one, right? Because I could draw a horizontal line there, and I would have lots of intersections, right? So that's not one-to-one. Okay, and so the typical restriction for the cosine is to go between 0 and pi. And so in this case, x is, oh, by the way, we have even symmetry here. And then x is between 0 and pi. Y is still between -1 and 1. Okay, and then for the tangent function has vertical asymptotes at pi over 2 minus pi over 2. It kind of comes like this and repeats itself. And so the typical restriction is to just restrict x to be between, whoops, doesn't include minus pi over 2 to pi over 2. Okay, and so then y is just a member of the reals. And so now that we've made these restrictions, we can now perform the inverse. And so we define the inverse functions, y equals the inverse sine of x, to be the inverse of the sine. And so the domain is going to be numbers between -1 and 1, and the range is going to be angle measures. Similarly for the cosine, the x values, what you put into the inverse cosine, are numbers between -1 and 1, and you output angle measures between 0 and pi. And so for the inverse tangent, you put in any real number, but what comes out is stuck between minus pi over 2 and pi over 2. Good. And so we're going to work with these quite a bit, but I just wanted to mention here, while we're talking about functions and their inverses, that you can actually define the inverse functions now without really working with them very much, because once you have the original function, you know what the inverse function is going to look like. Very good. Okay, I'm going to stop here, and then we're going to pick up next time on Friday with a little bit of review of trigonometry. So we'll continue from this trig stuff. All right, I'll see you then.